Good afternoon, everybody, and welcome to this final session on multiphase flow. We have 45 minutes for 3 presentations today, and I will be hosting it. I'm Yann Deloré. I'm based in Dublin City University in Ireland. Before we get started, I'd just like to point out, I'm sure you're familiar with the system at this stage, but you have on the right-hand side of your portal, your virtual attendee portal, you have a live Q&A box, a window, and you can enter your questions there. I will ask those questions to the presenters in turn, and we'll deal with that live Q&A as an intermediary. So the first person to talk today, and I would like to point out that there will be a 10-minute presentation followed by 5 minutes Q&A approximately. And I will have to keep to the 15 minutes overall to make sure that we don't run over time. So the first presenter is Milad Bagheri. Milad is based at Technical University of Darmstadt, and he has 2 co-authors, one from TU Darmstadt as well, and Holger, who is from the Cultural Institute of Technology in Germany as well. I'd like to pass you over to Milad now.
Hello, everyone. Can you hear me and see my screen?
Yes, we can, yeah.
Okay, perfect. So welcome, everyone. My name is Milad Bagheri. I'm a PhD student in computational multiphase flow group led by Dr. Holger Marshall. Dr. Marshall is from Technical University of Darmstadt. We are collaborating with Karlsruhe Institute of Technology, which we have Dr. Martin Warner from there. So here are the contents that I will be covering. The first one is that why are we extending our solver to cover more than 2 phases? What are the challenges involved? What has been done so far? Our methodology of extension, the library that is developed, and some preliminary validation results. So why are we extending our solver to cover more than 2 phases? The reason is the application areas that we are looking at. For example, if you look at the internal combustion engine and we consider one single cylinder, we can see that during the intake stroke where the droplets, fuel droplets are sprayed, we have tiny droplets that collide with the wall, which is lubricated by oil. These very high-speed tiny droplets are what we are considering. Now, the other application is in the exhaust gas after treatment, where the urea water solution or the AdBlue is added in the exhaust gas after treatment. Now, these very complex spray scenarios are the processes that can be simplified into a normal impact process. Now, the key parameters that dictate the morphology of the impact are the diameter of the drop, the velocity of the drop, and the thickness of the liquid film that we have. Now, more complexity can be added into this process if the liquid drop, the impacting drop, and the liquid film are made from different fluids. We can see that in this case, we need to consider the effect of immiscibility and miscibility of the liquids. I got some examples here from the in-house experiments conducted at TU Darmstadt. We can see that from top to bottom, we have low to moderate to high and to very high energy impact cases. We can see that the morphology of the crown forming and the dynamics is totally different. We have deposition, we have crown formation without generation of secondary droplets. We have, which is this case, we have a central jet, and in the last case, we have a crown formation with formation of a secondary droplets. Now, to make the process more complicated, let's see immiscible liquids. So we have a water, dyed water with red color impacting an oil. So these are immiscible. So we can see this morphology. We have instability at the rim, which generates ligaments, and the ligaments contain both the oil and the water droplets simultaneously in the secondary droplets. We have a mushroom-like structure, jets. And if the same simulation, the same experiment is repeated for the case where we are considering miscible fluids, we can see obviously totally different morphologies. Here is another experiment. We can see immediate generation of very small, tiny secondary droplets. We can see the mixing that is happening between the fluids in these experiments. And we can also see that the mixing is happening in the secondary droplets that are generated. The ligaments are a bit larger. And at the end, obviously, we are seeing a central jet, which this central jet is quite different from the mushroom-like structure that happened in immiscible liquids, which is appearing now. Now, these processes are very complex to capture. So the methodology that we considered in order to capture this dynamics is the phase fill method. Now, phase fill method is basically a physically is based on a physically developed method, which says that in reality, interfaces have finite thickness, and it's based on a variational formulation. Here, I got an example from sharp interface methodology, where we have the change of the concentration gradient across the interface. We can see that in the sharp interface, we have a very sharp transfer from one phase to the other. However, in the diffuse interface, we have rapid but a smooth transition from one phase to the other. This rapid and a smooth transition causes a concentration gradient. This concentration gradient will further contribute to the energy that is associated with the interface. Now, there are some natural challenges that when using diffuse interface, for example, you need to accurately initialize your phases. So this is exactly a tangent hyperbolic profile that not only it should be accurately initialized, but also it should maintain during the course of your simulation. The other complexity is that you're solving a fourth order partial differential equation. And this partial differential equation contains some modal parameters that you don't normally see them in the sharp interface methodologies. Now, there are extension challenges to end phase, which are mainly around consistency conditions. Well, reduction consistency should be maintained. It means that the model should, the end phase model should reduce to the two-phase model. Otherwise, you will have fictitious phases, like arbitrary, phases, non-physical phases appearing in your computational domain. And you really need to honor the thermodynamic consistency, the consistency of mass conservation, momentum conservation. You need to obey second law of thermodynamic, in which the direction of energy matters, and also the Galilean invariance of the methodology. So what has been done so far? On the left-hand side, you can see the experimental study from top to bottom, from low energy, moderate energy, and high energy impact. And on the right-hand side, you can see the numerical studies. These simulation results has been validated with the in-house experiments. On the right-hand side, you can see the adaptive mesh refinement that we are using. On the left-hand side, you can see the interface, which is colored by the velocity magnitude. We can see that we are able to capture the most dominant physical features, which is generation of the jet, or for example, generation of a dome structure in both experiment and the simulation with sufficient degree of accuracy. We are using the post-processing, the image processing toolbox of MATLAB in order to analyze the images. This is only one of the results that I got with me here, which is the crown height, but we have different results. For example, we have the diameter at the top of the rim, we have the diameter at the bottom, and many other results which will be published in our new paper. Also, these are representing the number of interfacial cells, and we can see that we are consistent with regard to the number of interfacial cells. We can gain more information from the simulations. Of course, we can locally visualize the velocity contours, and we can get more insights into the process of generation of a crown, and expansion and descent of this crown can be really explained with the help of velocity contours and local velocity profiles. Now, this methodology is extended to cover more than two phases. As mentioned earlier, we are using Cahn-Hilliard equation to model interface dynamics, and we are using Navier-Stokes equations to model the hydrodynamics. On the right-hand side, I have an example of a volume of fluid, the transport equation of the volume of fluid equation, the transport of alpha. We can see that on the right-hand side of it, we have a zero. But yeah, the main difference between the Cahn-Hilliard equation that we are using for interface dynamic is that on the right-hand side, we have a term. This term should be modeled. Now, the main parameters are the mobility, which can be translated into a diffusion coefficient or diffusivity, but in fact, it's quite different from that. And we have the chemical potential of the system, and we have, of course, the lambda parameter, which is the energy associated to the interface. We have, of course, the double well formulation, which should be extended to multi-well formulations. And we have the Navier-Stokes equation with the right-hand side modified, containing chemical potential and the gradient of the concentration that we have. Now, in order to extend this to cover n phases in the computational domain, we need to consider pairwise mobility contribution, such as this between the phases of P and Q. We need to also consider pairwise interfacial energy contribution between the phases P and Q, and we need to reformulate our chemical potential formulation in order to obey consistency condition mentioned earlier. Of course, the right-hand side of the Navier-Stokes equations, we cannot forget it. We also have to include the chemical potential, summation of the chemical potential through all the phases, and the contribution from the concentration gradient through all the phases. Now, this is the diffuse interface library that we developed. The methodology is developed in FOAM Extend 4.0, 4.1. The name of the solver is Phase-Filled FOAM. And the way it is implemented is to guarantee extensibility of the methodology. We are splitting the fourth order partial differential equation into 2 second order ones. This is the library. We have the base library of diffuse interface, and we have a multiphase system, which divides into subclasses. Each class models every single parameter that's shown in the governing equation. And for the phase-fill equations, we have the Cahn-Hilliard and Allen-Cahn. We are particularly focused on Cahn-Hilliard at the moment because of the conservation of mass that it guarantees inherently. And we have different methodology of solver, which is segregated and coupled manner, which was a very nice presentation yesterday about the coupled solution. This is one of the validation cases that I got with me here. This is famous to be the floating liquid lens problem. On the right-hand side, you can see a liquid drop of highlighted in green is floating at the interface between the air and the water, which is highlighted by red and blue. Now we can see that when the simulation starts, depending on the value of the gravitational acceleration and depending on the forces at the triple junction point here, we can see that the drop will stretch horizontally and will be compressed vertically. Now in this state, one can measure the thickness of the drop. This thickness at different gravities can be measured, can be compared with the asymptotic analysis with the exact solution in the case where zero gravity, asymptotic solution for the case where the gravity is dominant, and we are in a very good agreement for the moment. Of course, more work to be done. So
we just have a minute left.
Okay, so concluding remarks, we need to honor the consistency condition. We have noticed that at higher speed, at high dynamics, we need to account for non-equilibrium interfacial energy, which means non-equilibrium surface tension contribution. We are validating our solver for more than 3 phases, and we are extending our solver to cover miscible fluids. This is our website. This is our YouTube channel. Feel free to subscribe. These are the papers that we are are published, and the first one we are working on currently. And last but not the least, I would like to thank German Research Foundation for founding this project. And I think my time is up. Thank you.
Thank you very much, Milad. Just like to remind our listener that the live Q&A is open. I see there's no question currently, so I will ask one. I would like to go back to the graph where you were showing the comparison between experiments and your numerical solution, where this one here. And I was just interested to know, and perhaps I misunderstood what NC stands for, but I was curious to understand why you had that step type of response towards the peak with the yellow curve.
Okay, so the NC stands for, maybe I can show it here. So this is how you have to in diffuse interface, you really need to capture the interfacial layer with sufficient cells. So if you look closely, we have this NC. This is what's referred. It's approximate number of cells that are used to basically resolve the numerical cells for that simulation. And the step. Well, the step of this, you mean, for example, for 12, you have a. That's correct. Yeah, there's a. Well, of course, this can be checked, but overall, it's I believe it's in a good agreement. Why is that happening when the number of cells? I don't think that will be a very huge difference. We are looking at a gap which is less than 0.1 millimeter.
Yeah, I must admit, I'm really focusing on something very, very small, but I was interested because it seemed to me that that wasn't happening when you had a lower resolution of the interface. And I just was curious to know if you had any insight into this phenomenon.
Not really.
Okay. Right, I'll give viewers a little bit more time to raise any further question.
Just questions there. If you refresh the page, they should come up for you.
Oh, okay. I haven't had that issue previously, sorry. Oh, there's actually a lot of questions. My apologies. So the first question, are the experimental data performed at TUD on splashing available for comparison purposes with VOF?
Yes, these experiments, which are conducted at Technical University of Darmstadt, currently by Bastian Stamp, my colleague, currently is working on developing his MATLAB script in order to basically tell us the composition of the secondary droplets that are generated, which can further be valid. We can validate our numerical simulations with them.
Okay, so perhaps you could I'll respond and continue that discussion in the discussion forum and point to, I presume it's available on your website, but if there is any further information about publication and so on, it may be useful to add that in the discussion forum.
Yeah, sure.
I will, I'm afraid there appear to be a lot of interest, so that's obviously a good thing. But I'm going to ask just one more question, and then I'll direct other viewers to the discussion forum and perhaps to bring those questions back through that portal so that you can keep the discussion going. So the next question is, are you able to compare numerical and experimental data for the impact force of the droplet? In your case, this is a severe test for your numerical model.
The impact force, well, what does it mean by impact force? What we can compare is basically coming from the image processing of MATLAB. We can compare a lot of things, but did we really consider to compare the impact force necessary for us? At this stage, it wasn't really necessary. I know it's a very harshly dynamic case, but at the moment, we mainly focused on the height of the crown, their diameter at the rim, the diameter at the base, the angle that they make, which are not shown in this just because I'm presenting what has been done so far. But maybe this could be also somewhere to go to compare the force at the impact.
Okay. Thank you. And
thank you.
I'm really sorry. There's one other question there. If you can answer it in 1 minute, maybe worth. Have you compared this approach with multiphase into form, which also consider 3 or more phases? And I'll stop there after that.
Yes. Well, we have a master thesis student now. Possibly he will work on multiphase interform, but the problem with is the surface tension formulation. The reason that we selected this methodology is the formulation of surface tension, which means that we don't need to calculate the normal to the interface. This will really help us in order to have better results if we would like to consider the generation of the secondary droplet, particularly the mixing, which is very difficult to, if we would like to extend the methodology for miscible fluids, we need to deal with interfacial energy. And this is not a concept that is governed by interform, because interform works with calculation of the normals to the interface, but you really need to consider the energy associated to the interface to really understand what's happening for miscible and immiscible fluids.
Okay, thank you very much. I really must, I'll thank you and move on to the next presentation.
Okay, thank you.
So our next speaker is David Barreiro. He's from Universidad de Coruña, apologies for pronunciation. And there are 2 co-authors, one from the same university and one from the Von Karman Institute. So I'll hand you over to David now.
Hello, can you see my screen?
Yes, we can. Apologies, no, we can see just your image rather than your presentation.
Not yet?
Not yet, no.
Okay, let me check. Sorry for that. Yeah.
Can see your background screen.
Yeah. Should be now.
Yeah, you're good to go.
Okay, perfect. So thank you, Jan, for the kind introduction. In today's talk, I will present an application of OpenFOAM to study the gas-liquid interaction in the jet wiping process. The jet wiping is a coating technique used for several applications, but we are mainly focused in the hot dip galvanization. And the process is sketched here on the left. The steel strip dips in a coating bath with molten zinc, and as it emerges from the coating bath, it drags a coating layer on its surface due to viscous effects. And a slot gas jet, as the one shown here, is used to reduce the coating thickness to approximately 1 order of magnitude lower than the drag-out thickness. Here you can see an image of the industrial arrangement with liquid zinc, the steel strip, and the gas jet nozzle. The galvanization lines are controlled by several parameters: the standoff distance, zeta, the opening of the nozzle, D, the pressure inside the stagnation chamber of the nozzle, and the velocity of the substrate. The effect of the gas jet on the liquid film is given by the wiping actuators, which are the streamwise pressure gradient and the shear stress at the interface. The problem of this technique is that there is a gas-liquid interaction that is highly unsteady, and this leads to the formation of long wavelength patterns in the final film. These are known as undulations and have a high impact in the product quality. In this work, we numerically investigate the mechanisms responsible for the formation of these structures in the liquid. So this presentation is driven by the following questions. First, can we use CFD simulations to investigate this complex problem? And to answer this, we use the 3D VOF-LES simulations with OpenFOAM and experiments to validate the model. The second is we want to identify the main features of the liquid film dynamics, and to this end, we analyze the time-dependent thickness distributions obtained with the CFD with the multiscale proper orthogonal decompositions, since this is a very helpful tool to detect coherent patterns. And finally, we want to close by answering the following question: what is the main mechanism of undulation? We use the mPOD and extended mPOD to correlate the film dynamics with specific structures in the gas flow. So in this section, I present all the methodology needed to answer the previous questions. We reproduce 3 wiping configurations experimentally characterized in the literature. The simulations feature 3 different configurations, 2 different standoff distance, and 2 different gas pressures. And the liquid is the propylene glycol, and the gas is air. Here you can see some animations about the time result PIB of the experiments and the light absorption method to detect the gas-liquid interface. So we simulate the 3D wiping configurations with 2-phase incompressible formulation in the interfoam solver. I will go very quickly through the mathematical modeling, as it is a very well-known solver in the OpenFOAM community. Basically, we solve for the transport of an extra variable, which is alpha, commonly referred to as a liquid volume fraction. And in this model, we have an interface compression term, which is only active at the interface to limit the smearing of the interface. The behavior of the gas jet is modeled via a large eddy simulation, in which the turbulence is filtered. The large scales are resolved, and the subgrid scales are modeled with the Smagorinsky model. Due to the high computational cost of the simulations, we had to ask for 2 periods of 4 months in the Spanish supercomputing network, spending 3 million CPU hours in total. The domain is discretized in a 3D structured mesh, built-in block mesh. The different boundary conditions are represented on the left with colors. The moving substrate, the coating bath, and the jet nozzle are modeled as walls. The boundaries in red are outlets in which we establish the atmospheric pressure. And the inlet of the gas flow is here in blue, where we set the nozzle pressure. On the right, you can see a detail of the mesh in the region of maximum interaction, where we tried to keep a good resolution in order to capture well the jet dynamics and the gas-liquid interaction. Here I will compress a lot the fundamentals of the mPOD. The mPOD is a data-driven decomposition, so that no basis is defined a priori. It is basically an energy optimality decomposition as the POD, characterized by frequency constraint modes. The decomposition breaks the data as a linear combination of elementary contribution, which are called modes, and using this matrix representation, each of these modes have a spatial structure, temporal evolution psi, and an associated amplitude. To give comparable weight to the runback flow and final film, we perform a normalization process prior to the modal decomposition. Hence, both final film and runback flow have comparable energy, or which is the same amplitude. And therefore, it will be easier for the decomposition to detect the features that are in common between both regions. For the extended mPOD, we follow the idea presented by Borrev with the extended POD. Then the idea is to find correlations between the film patterns and the gas jet dynamics. We take the temporal structure of the liquid decomposition, as the one I represent here, and we use it as a base to decompose the data of the gas jet, the velocity and pressure fields. Therefore, we can rebuild the spatial structure in the gas that are strictly linked with the formation of the undulations. Now it's time for the result section. On the left, you can see a 3D reconstruction of the film for cases 1 and 3. It is remarkable that featuring very similar wiping numbers, the flow dynamics are very different. In case 1, the film is much more two-dimensional than in case 3, where the runback flow becomes fully 3D. The average thickness is computed in this red window near the outlet, and on this table you can see the comparison with the numerics. The trends of the thickness are correct, and the agreement between the experimental and numerical values is satisfactory. But it is true that the numerical model tends to underestimate the final thickness, but this tendency was also observed using very similar CFD simulations in the bibliography. In terms of frequency, the power spectral densities are computed from the leading mPOD modes. And overall, there is a very good agreement between both experiments and CFD simulations. What is very remarkable also is that we systematically detect a frequency peak in common between the final film, runback flow, and gas jet. And this is a clear footprint that the jet is coupled with the motion of the liquid film. The multiscale analysis of the film shows that even when the dynamics of the film are very complex, see, for example, the original data of case 1 and case 3, we always detect a dominant pattern of two-dimensional waves present in the entire domain. These are waves that share the same origin near the wiping and travel in opposite directions. Moreover, if one looks at the spectra of the gas jet, now on the right part of the slide, it can be seen that the frequency of this pattern matches perfectly the frequency of the gas jet, which suggests again that are in fact coupled these two phases. We call this component of the liquid film the 2 decoupled undulations. And the extended mPOD also revealed that the 2 decoupled undulations are correlated with a shading of vortices here near the runback flow. This was also detected in the PIV in the experiments, but not fully captured because of reflections. In reality, when you add back the mean, you can see that it is in fact correlated with a deflection of this side jet attached to the runback flow. In order to link the gas jet motion with its time-dependent wiping capabilities, we also apply the extended mPOD to the wiping actuators. Qualitatively, we can see how their evolution is strongly coupled with the formation of waves. And in this sense, it is found that the main source of instability in the wiping actuators is a pulsation of the pressure gradient associated to the runback flow. So just to conclude, I come back to the initial questions. So the CFD simulations have been validated in terms of the main features of the film and gas dynamics. We found that the wave patterns are essentially two-dimensional in origin, even when the flow in the liquid seems to be 3D. And we named this pattern the two-decoupled undulation. And finally, we extended the mPOD to correlate the undulations with the periodic deflection of this side jet in the gas. Most interestingly, we found that the main source of instability for this configuration is the pulsation of the pressure gradient, which periodically modulates the wiping efficiency. Despite this was not asked at the beginning, we found that the velocity profiles inside the liquid film are parabolic. This is very remarkable for future work because it's one of the assumptions made in the derivation of simplified integral models. And just to finish, as future perspective, we are going to use the validated model as a, let's say, numerical experiments to investigate the wiping in improved similarity conditions with water, because from the liquid side we can reach conditions very close to the industrial galvanization lines. This is the end of my presentation. Thank you for your attention, and now I hope we have some time to answer your questions.
David, thank you very much for a very interesting presentation. We have one question from Kent Wardle. Question is the gas jet 2D or made up of many small 3D jets in a linear array? Is the gas jet always normal to the film surface? And is that a parameter you will investigate? So 3 questions there. Sorry,
I will refresh. But basically, the jet is like an air knife. It is planar, but the simulations are, of course, 3D.
Okay. Another question from Andre de Luz Moreira. Very nice work in simulations. What kind of boundary conditions do you use for the jet? And say hi to Miguel for me. So you've got the message passed.
Okay. I will do it. So the boundary conditions for the jet, we use the pressure in the stagnation chamber, because we also simulate all the channel. But in the new simulations with water, we are planning to use let's say more complex boundary conditions, because we reach a more, let's say, more turbulent flow in the jet.
Okay, thank you very much, David. There's another question on the LES modeling, which is very important. So I'm going to ask Richard if you could pass that on through the discussion forum, because we're just running out of time. So okay. I will take that as being answered, but please copy it into the discussion forum. So thank you very much, David. Our next speaker, and I'm afraid we literally will have 11 minutes, is sorry, the name is not the one I had. Francisco Bodisky, apologies for the pronunciation, who is from Technical University of Darmstadt as well, with a co-author from the Max Planck Institute for Polymer Research. So I will pass on the mic to you straight away. Francisco, thank you very much.
Yeah, so I'll share just my screen. Can you hear me well and see me also?
Can hear you very well, and we can see the presentation now. Yeah.
Okay, great. Even if it's in full screen, is it fine?
It is in full screen. Yeah.
Okay,
thank you.
So let me put the pointer. So hi everyone. Thank you all for joining in. So I'm Francisco, and today I'm going to talk to you about the motion of droplets in inclined surfaces, in which we have studied this for the diffuse interface Faisal method in conjunction with the experimentalists in the Max Planck Institute. As a side note, I don't speak as fluently as the other participants, as you will sort of notice. So if I say something which you don't understand, just let me know and I'll try to be clearer. So a brief sort of motivation. So as we all know, sliding droplets are widely sort of seen in various sort of applications, such as self-cleaning surfaces, also in microfluidics, and also in water collection. So some insects are able to thrive in the driest sort of regions, because their their sort of shell or exoskeleton is made up of hydrophilic in highlights of hydrophilic surfaces at which the water will sort of accumulate, and after it's big enough, it will slide down into its mouth and you can drink it. And this is the motivation behind the water collection via fog or air. So because of this, the study of the motion of droplets is very interesting and also very important. But the correlations and the physics behind this is not very well understood, especially the dissipative forces happening at the bulk of the droplet and near the contact line, and also the contribution arising from the rear and the front part of the droplet are not very well known. So here is an experimental setup in which we have based our simulations from. And here is a video of droplets of water droplets sliding down a 40-degree inclination angle. I'll show it again. So as you can see, we are trying to simulate this sort of behavior. So first of all, I will talk to you about the governing equations. As my colleague Milad has explained, we used a phase field method and our in-house solver called phase field foam. So I'll try to be very brief, as it was mentioned already. So we assume here we have a mixing of the components at interface width. So phase 2 and phase 1 are separated by another parameter, and it will change via some sort of gradient, a sharp gradient, but still a gradient from one phase into the other. And by having this, it's possible to specify the free Helmholtz density, the free Helmholtz energy density, to model the mixing energy. So here we have the interfacial energy and the bulk energy, and by having this, it's possible to obtain the chemical potential of this system. The chemical potential is the driving force that moves the interface, and so it's set on the right-hand side on the momentum equations. Also, we have this equation, the Canillard equation, in which it models the evolution of this interface. A very sort of interesting and useful behavior or formulation coming from this is a boundary condition that arises via some sort of energy formulation, in which we only have as an input the equilibrium contact angle, and as the dynamic answer of the system is going to be the dynamic contact angle. So I'm going to show you now some sort of numerical aspects. This solver has been enhanced by a moving sort of reference frame, so MRF, by the addition of an acceleration term in the left-hand side of the momentum equations. And this allows us to, so here is the animation of the MRF. So this allows us to do these simulations while the droplet is sliding down, it stays in the same position, and this will save us a lot of computational domain and also power. And the position of the droplet is controlled by a PID controller, in which it will sort of regulate the wall velocity to keep the body center in the same place. So here is the computational domain. As you see, I'm using AMR over the whole volume of the droplet, and this is because we are also interested in the fields inside of the droplets, so the energy fields and the velocity fields inside of this droplet. From this, it's possible. From this, I'll show you some a brief animation of a sliding droplet. So as you can see, it first sort of wobbles because of how it is initialized and because of capillary waves. Afterwards, it starts elongating, and I don't know if it's possible to see in your screen, but it's possible to see some contact angle hysteresis. These sort of results are then compared and verified with experimental sort of results from the group of Hans-Jürgen Butt and his team, in which we check if the velocity profiles, the steady state speed, and the contact angle hysteresis are similar to our sort of results for a water-air two-phase system. So the equation of motion for a sliding droplet is given by the Newton's equation, in which the first term is the inertia or the acceleration term. The gravitational force is the driving force. It drives the droplet downwards, and it's counteracted by the viscous force or the viscous dissipation, which is acting on the whole volume of the droplet, and also by the capillary force, and this is only acting on the contact area of the droplets. But if the droplet is also sort of rotating, is this equation going to hold still? Well, more or less, we have observed that if we have a sort of rotational component inside of the droplets, we have to use an effective mass, a droplet effective mass, because since it's also rotating, it will have a higher effective mass compared into its real mass. And so the final equation, it will look like this one. This m star is calculated from the kinetic energy fields, in which the transitional component is given by this term, and it's calculated from the sliding speed, and the rotational component of the energy is given by the volume average, or the volume, or if you want, the volume integral over the whole volume of the droplet of the kinetic energy density field. This will give us the m star value, or the droplet effective mass. Since we are short on time, I'm just going to show you another sort of result, in which we have compared the contributions of the rear and the front part of the droplet with the contribution, and their contribution into the energy dissipation. And actually, some correlations exist in which they try to sort of estimate the contribution of the dissipation rate for the front and rear part of the droplet by this C parameter. So so this C parameter is inversely proportional into the contact angle. So by this correlation, we would expect that the rear part, since it has a lower contact angle by the receding angle, it will have a higher dissipation rate, and thus a higher contribution into the dissipation forces acting on a droplet. This is exactly opposite of what we see. In fact, the front contribution is almost twice as high in terms of the energy dissipation, and the causes of this are two main causes. The first one is that these correlations assumed that the droplet shape is somewhat well behaved, or it's, if you want, half hemisphere, so it's not very skewed. And also the rear and front edges are assumed to have the same shape, which we do not have, as you see here. So here, for a 40-degree inclination angle, the droplet is quite skewed, and actually, if you increase the inclination or the speed of the droplets, this will deviate even further and further because of the because these assumptions are not confirmed, I guess. So
it's just 1 minute before the end of the session.
Yeah, I'm finishing up. So concluding a sort of remarks and future scope. So the droplet effective mass is should be considered if we are accounting for droplets which are sliding and now sort of holding for a long period of time, as their contribution of the rotational part is no longer negligible. And also the viscous forces play a very important role, and also the shape of the droplet, it plays a very important role in the viscous forces, which is not accounted for. And so for a future scope, we plan on improving the current correlations by the addition of a shape factor, and also investigate the contributions of the rear and front parts, contributions for the viscous force, and finally have a look at more complex substrates. Here are the 2 papers in preparation for this study. And thank you all. I hope you enjoyed the sort of workshop as I did. If you have any questions, ask me in the chat or email me or my supervisor, Holger Marshall. Thank you.
The session is finished, and I don't know if attendees are still able to hear or contribute. Can I check with moderator?
Yeah, no, we can still hear.
Okay, thank you very much. So we do have a few minutes. So the first question I have is, can this model also consider a droplet between TWO surfaces?
Between two surfaces?
Yes. Sorry.
Yeah, no, it's fine. Yes, and we are sort of actually studying this as of now. So the idea is to change the phobicity of these substrates. So I have a hydrophobic part, hydrophilic part, etc., etc. So yes, it should be possible to do this, and we are actively doing this. And then I have another question: is the PF solver available open source? Yes. I mean, I'm not sure if the MRF is available open source, but if you could contact me, I can try to see this.
I have one final question. Well, on my side, I would love to ask you if you've considered looking at dynamic contact angles and their effect, or if it would be justified at all for this type of droplet flow.
Actually, this is not so. Part of our formulation doesn't need dynamic contact angle as a boundary condition. So, as I've explained, the boundary condition arising or the order parameter only has an input the equilibrium contact angle, and by having this and the contact line speed, it's possible to model the dynamic contact angle and also the hysteresis.
Okay, so it is a dynamic contact angle formulation in itself.
It's already yes.
Okay.
Thank you.
So I'm just going to add that there are a good few questions in the discussion forum. I haven't checked who they are from, or but I think it'd be worth for all the authors here to or presenters to check it out in case it concerns you. Can I check with whether we simply close the call at this stage?
Yep, I can close the call.
Okay, so I only see now that, yes, obviously the sessions can run over. So I just like to take this opportunity with time to thank you all for very engaging presentation. I know the last author was saying that he wasn't as fluent, but clearly was very, very capable of presenting a very good presentation. And that's been the case for the three of you. So it's been very pleasant to listen to you. And I have no doubt that would have been the experience of all of the people attending. And it's a nice way, from my point of view, to finish the conference. So I'd like to thank you again and to thank everybody attending today. It's been a pleasure.